So, good morning. Second lecture. And first, I don't know, some questions from last week? If not, I would like to show. I'm not sure if I showed it last week, but there is a web page for this course. And there is a lot of information. One thing is the weekly lecture plan, which, oops, I'm clicking strangely, like this. And what you see here, now let's see, oh, now it comes. Yes, it's alive. So what you see here is a list of all the lectures. There is a link to the notebook that I'm using for the presentation. It's presented as slides, and there is also PDF generation, which includes all the notes that are in between, which I don't show during the lecture. It's more text to explain what the slides are about. And I also do recordings. That's why I use my headset. So you can go on YouTube and listen afterwards on the lectures if you want to do that. There is also a link to the exercises, and if you look very closely, you can see that the new lectures, they are the typical YouTube logotype, and if not, there is a spider web on it. So that's last year's lecture. So you can even listen in advance if you like. Yeah, and then you have all the dates for this. Yeah, so let's skip over to today's lecture. Can you do it like that? So, today I'm going to talk about data sets and different aspects of data sets actually. And we want to look at some famous data sets, so not even your own, or maybe you're also famous, I don't know. There are different types of data sets, and then we're going to look in what makes a data set good or bad or useful. And finally, it's also about building your own data set, how you can organize your data a bit, and what to think about. And what is more is we're going to look into augmentation. So when you have too little data, how you can boost it a bit, make it a little bit larger. Then a little bit about algorithms, actually baseline algorithm. And I'm going to show some examples on that. And I think it's not in this list, but anyway, I'm also going to give a little bit technical introduction to something called data frames, a tool that is quite useful when you want to organize your data. So let's start getting this one run. And here we load a couple of packages. Sometimes you may get warnings if something is not completely up to date. On the Mac, there is often TensorFlow warning flashes, but usually you don't have to mind about that, but they may come up. This TQDM is just a progress bar, so if the progress bar doesn't show up nicely, that's the reason. Then we have some references that you can read if you want to take a look at. So the Python machine learning, there is even a special chapter dedicated to building data sets. And then you can also look into standardized approaches for preparing, so people use the same approach when they build their data sets. And then there is even more. There is a little bit about augmentation tools. There is always coming up new tools, so this list is actually not so up to date, but there are some tools that you can look at, how you can augment and also how you can annotate your data sets. So first, we're going to look now at some known data sets, and you can maybe ask, why do we have to look at other people's data sets? And The reason is they are there. You can use them. And very often they are open, and people have already put a lot of energy into making them prepared, categorizing different classes, marking up, and so on. So you don't have to do it. And if you're lucky, there are people who actually have marked up more or less the same features you would want to look at. Or maybe not, but then at least you have the images, and images are expensive, in particular if you do it in a scientific environment. Maybe you can only get 1 or 2 days of beam time, but you would really like to have correspondingly a month of beam time. And with that, with the external data sets, you can actually get that information. And there are some comments, meanwhile a bit old, but anyway, this guy, he says that he has created loads of algorithms, but in the end, the most knowledge he can extract is actually from well-prepared data. And another one is an example. Tesla is today not very popular, but anyway, they do a lot of machine learning, and they put a lot of energy into preparing the data sets for their training, and then finally doing some models and algorithms. Some people during their PhD, spend all the time and all headache on getting the best and tuning the best algorithm, and then a little bit on data because they don't have so much. So that's a contrasting view of how people work. And here is another. There's a lot of tweets here, and then finally, she comes to the point that 95% of her time is about actually creating and cleaning and making a nice data set to be sure that they can work with the algorithms afterwards. And the remaining 5% is about plugging it into the algorithms and work like that. So data is of course important. That's what we want to do our science with. But and it's actually useful for different purposes. One thing is to test your algorithm, maybe even before you have your own data. So you don't know if you have a data set, of course, that's measured, but without the knowledge, your expert knowledge, it's not worth so much. So you really need to know a ground truth within the data. And also, you have to make sure that the data, I'm coming to that later, you may only have some extreme cases because you didn't have resources to do all it, but you need to make sure that your algorithm is actually working on each of these edge cases. And then in the big company context, they actually evolve their algorithms every few hours, and to make sure they actually do what they want, you need to have something to test that they actually work in the right way. And for machine learning purpose, when you do machine learning, you really need to have good data for building your algorithms. You don't know if the algorithm is doing right if you don't have the right kind of data. So if you want to try to detect small changes in the cell structure, or you want to see if that indicates a cancer, you can probably not write a list of these rules yourself, or in some cases you can, but mostly the changes are so subtle and so individual between each case, so you need to have a lot of background to be able to sort that out. And there is where the machine learning comes in, because it can see the trends in all these cases. So hopefully data is reusable, or that would be actually a task when you do your measurement, to make sure that it can actually be useful afterwards. And that makes it also possible to have a better base for continuing continued work with this kind of data. And algorithms, well, they can often be prototypes. You have your little task in your project. You want to write a little algorithm that sorts out your problem. And the characteristics of a prototype, it's unfortunately usually messy. You don't think about coding styles and other things when you write your first prototype. You want to have it working. Often it's overly complicated. You can, in later optimization steps, probably make it much nicer. And it's also poorly written. It's like in the spur of the moment, you see, I need to change this one and this one. And this is typical workflow when you do your first algorithm as a student, getting your data. You try to do something. Even when I try to get my first prototype, I'm not very structured. I want to have it working. I want to show the proof of principle. With experience, you can, of course, make it cleaner, but in the beginning, it is under time pressure, so you do what you can to prove your principle. So under these conditions, it's good if you have at least data that you can rely on, because then you can test, does it work? Does it improve? Is there something that can help you to improve your algorithms and get on with your project and get your data out and the statistics later. Some famous data sets, they're probably not so relevant for most of you. Looking at your backgrounds in your enrollment list, I don't think you're so interested in cats and dogs or just numbers, but that's a typical machine learning starting data sets that people start working with. And in this case, we have the MNIST digits, we have ImageNet. One that could be more interesting for you is the BRATS dataset, which I'm going to show a little bit later. But it's starting points to get your machinery running. And the MNIST dataset is very nice. It's just a bunch of handwritten, labeled numbers. And they are also black and white, so you don't have to do any pre-processing. The people who prepared this dataset, they did all for you. And it's a good starting point, at least, to get an idea how your algorithms may work. But I think identifying numbers is not what you are looking for. The ImageNet is a much larger database, and it's also categorized into different categories. So you can see here, there is a hierarchy. Probably you don't see it because it's so small, but anyway, you have object, substance, matter, then you have organisms, you have artifacts, you have food, and so on. And then you can see here there is even fruit, vegetables, and plants get fruit, so then you can have a double relationship. And over the years, with development of different algorithms, you could improve the level of precision. And in the beginning, they had very shallow neural networks, so that's the basic unit of the machine learning, one of the basic units. So then you had only a neural network with few nodes, and at some point when they got more computational power, thanks to the graphic cards, they could make much larger networks, more complicated, and then they get more and more precision and can improve the results. So what can we learn? We have different approaches on how to work with the data. Mostly people are doing experiments. They are in this corner, so they do their own identification, they do labeling, they have expert knowledge within their field, whatever that is. Could be civil engineering or biology or physics, geology, something. And they know exactly what they are looking for, and they can help marking up things. They can also do this approach that they know what they're looking for and tailor their algorithms to doing that. With the evolvement of the machine learning and data science, there was a new approach. Teenager boys in the basement could, with their gaming computer, without any knowledge, start getting good results on segmentation problems because they had this deep learning approach. So they knew how to work with the algorithms. They took some data and they could produce some results. But they don't know about what they are seeing, actually. So to do the real science, you have to have a mix. You have to have the knowledge within the field. And then you can boost your results with the help of these algorithms. And probably also with help from some people who know how to tame these beasts and how to get the best out of it. So, do the machine learning approach always win? Well, it can get good results, but the important thing is actually any kind of image analysis you're doing, it's good to have well-labeled, structured, and organized data sets, because that is where you can test and be confident that you actually do the thing you want to do. And what kind of algorithm you use doesn't really matter. It's more the validation step that is the important one, and for that you need these test data sets. And then there is a problem, actually, when you work with other people's data sets, they're cured for the other people's needs. So sometimes you don't know all the tricks and features within the data set, or maybe it's not even labeled in the same way. And this Kasi Kozilovsky, I can't even pronounce her name. She made a couple of nice statements. So inherited data sets is like using someone else's toothbrush. Using them is an act of desperation. You have to brush your teeth, so take whatever you have. And sometimes it is like that, but you have to see that in the light of collecting your data is actually also very expensive. And if you can have something that can help you, then it's good. And it's also easier to get already made data, but you have to gain its trust. Oh, it has to gain your trust, actually. So when you take a data set from someone else, you have to make sure that it actually is useful for you and that you can work with it. Another thing is data set ethics, and in particular when you work with medical data, you really need to look into this part. How was the data obtained? Do you have all the ethical parts, like what's it called? Consent from the people who share the data, the patients in the end. Do they consent that you use it for your even put it as open source? Is it anonymized, etc.? And then you have to make sure that there is no bias in the data, so it can be misleading for later investigations. Also looking into the integrity and avoiding manipulation of the data. And then sometimes there are even ethics commissions looking into who is going to use this data or who is allowed to use the data. One example is at CERN. They produce vast amounts of data, but they have a committee where you have to apply to get a certain fraction of the data set, and you have to even motivate what kind of science you want to do with it, if it makes sense, if you are allowed to use the CERN data. And I assume there are similar things within the medical applications, that if there is a large database, that you have to really check that the data has the right origin or is used in the right way. And of course, what you have to do if you create your own data set is, of course, get the consent from the people or the organization that you get the data from. The data must be anonymized, so you cannot connect it with anyone anymore. Then possibly, depending again on the application, using ethical review committees for getting access to the data. Then you need to also bundle it or store it in a way that it can be available, but only when it's granted. Another thing which has grown over the last, I would say, 10 years is promote open and fair data. I'm going to fair in the next slide. And then also having audit processes to avoid biases and make sure that the data is fair. And finally, also document everything that is allowed to be documented, but the whole acquisition process and how it's done, what kind of equipment you use, under which conditions, everything should be documented in a way that people can actually use it afterwards. The FAIR principle is something that was introduced in this paper by Wilkinson et al. And there are 4 base requirements for open data. And the first criteria is that it's findable. So there should be databases making it possible, maybe even providing each data set with a DOI. Then it should be accessible. So there should be some kind of portal that allows you to download it, or at least giving you the possibility to get the data. I don't know exactly how, or maybe you can just go on the repository and work directly in the repository. There are different approaches to it. And interoperable may sound a little bit strange, but is that the data should be possible, and actually also software should be possible to apply on different platforms, different data formats, or that the data formats follow some standards that you can actually transfer it between different places. The final one, reusable, that's good if it's possible, but it also requires that you do document with a lot of metadata that the data is, that describes how the data was acquired, under which conditions, each experiment step that resulted in this data. And in this FAIR principle context, there is also even an organization within the large-scale facility that works on an open science cloud for photon and neutron sciences. And yeah, there's a link so you can click on it. Actually, also Wilkinson is also a link so you can get to that paper if you want to look into that. I have started to look at data sources that may be of interest to you. Right now the list is quite short, but on the project, the course webpage, you have data sets. I will expand that also with literature later, possibly also software packages, so you have a collection of these tools. The ones I have here, I give the title and the link, describing it and telling which kind of license and the date when I added this data set. When it comes to IEEE data port, some of it you can just fetch. The other ones you have to be an IEEE member to access it. But it's a quite big collection of very various data. Then the EPFL Computer Vision Group, they have some nice prepared data sets on the GNU public license, so that's freely to use. The Google Dataset search engine is not so sorted, but you can search in the normal Google way, that you just look for data sets, whatever kind you want to have. And then there is, this is a list actually of data sets that are available in the field of medical imaging. But I will add more when something comes across me. One in medical imaging that is quite known and well maintained is the BRATS, which is tumors in MRI brain images, where they have the MRI images and they have also marked up different features in the different modes of the MRI. And with that, you should have quite a lot of information for identifying tumors in the brain. So what makes a data set good? So first of all, a good data set, to be able to work with it, to have a useful data set, you need a lot of data, because data is needed for statistics, and the more data you have, the better statistics you can achieve. Also, diversity. You should have all the variations, and annotations. In some cases it's not needed, but in other cases you need to also label different regions or images in different ways. So first of all, you need a lot of images, in particular if the content or the problem is complicated, and it can be also very subtle differences. So tumors are not very easy to find. The radiologists, they were looking at some images, and those who did the planning, they couldn't understand what the doctors were actually finding. They just marked up something, and then the planners, they saw, okay, that is what he wants. And it's not very easy to see it, and it requires a lot of experience to actually extract these, so because of the very subtle differences. Another problem is also class imbalance, which I'm going to talk about soon. But of course, if you don't have a lot of data, use whatever you get, but let it grow if you can. Lots of diversity. So usually there is a lot of variation within patients, within symptoms, within different kinds of samples. Nature is great variety. So, and there on top of it, there is lots of algorithms. There are different acquisition conditions like noise levels, illumination types, also orientations of the objects, maybe colors, and so on. And there will be also a lot of, you also need a lot of examples from each category. So for example, there is male breast cancer, but the cases are so few that it's very hard to get a statistical support for it. So it's hard to generalize it. And then meaningful labels. So of course, the labels should fit your task, and there should not be any ambiguity, so that one labeler would say, no, it's that, oh, no, it's that, says the other one. But it should actually, all labelers should be coming to the same conclusion. Shouldn't be too obvious, for example, that the standard deviation or something like that, or the histogram, is not meaningful for labeling, because you can just compute it and then you don't need to put a label on it. And it should be derivable from the image. So looking into patient data, it doesn't matter to the image which health insurance you have. You can't see it in the image, usually. So that is useless information as a label. It's relevant as metadata, but not as a label. And ideally, you should also have some quantitative feature in the labels. So we have different purposes also of the data sets, or actually it comes to what kind of analysis you want to do. And here you see a list. I'm going to actually look into them, each one of them, so I'm not going to say so much more on this page. So classification is one, where you want to take an image and put it into a category. For example, is this a dog or a cat or something like that? And each image can only have one category. And they should be non-ordered, non-ordered usually. So for example, you can have cat, dog, cancer or healthy or something like that. You can also have multiple classes, but in this case I only have two classes. So this I hope works, but this was one that, it comes. So here you have the example. I loaded the MNIST, and as I said in the beginning, there comes a lot of, I think it's only just log information, but it looks a bit messy here. But anyway, what you can see, we have all these numbers from the MNIST, and what you can see also is that we have a 4, and it's actually labeled as a 4. Here you have a 1, 0, and so on. So this would be the task of the classification, that given an image, you should get a number. And regression is taking an image and from that estimate a number of something. So here are some examples: the value of a house from a picture, or the risk of a hurricane from a satellite image. That are typical regression tasks. Here is one which is, I think is a Kaggle example, where you have radiographs from hands of children, and with it you also have the age of the child. And the regression task is from a radiograph, telling what is the age of that child. And then we have segmentation. Then we, in contrast to classification, now we have to look and identify regions that correspond to some specific class. So on this picture of dogs and cats, the idea of the segmentation is that you should be able to mark where you have these animals, or which kind of animal you have here. And other cases would be if there is a tumor or not in the lung of a radiograph, or extracting straits, or the cats and dogs. One example would be to look at microscope images and find nuclei. And here you have the microscope image of some stained cells, and then the task is that you label each one of them and identify where you have them, to do possibly some measurements on them later, which is what we're going to do in a few weeks. Detection is also to find if something appears or not appears on the image. It doesn't really need to be very precise contour, but just saying in this region there is something, like possibly a car, or in this case looking at opaque regions within the X-rays. And as you can see here, you have some boxes which are marked out as critical according to some criteria. And then there's a lot of other tasks that you can also do with these data sets. So there is a list on this one. There is kind of a distinguishing between horses or zebras. Another task that you can also use the data for is to test your image enhancement approaches. So in particular doing denoising, because it's not always that you can get images at the quality you want, and to remove the noise is actually a big task, which I'm going to talk about next week. Another thing would be to go into super resolution, being able to look at how can you improve the resolution of the images in different ways. And for that, it's also good to use some data where you have a ground truth, say a very high resolving image, and then you downsample it or degrade it to some degree and see if you can get back to the high resolution. So, building your own data sets is, first of all, very time consuming. First, you need to do the whole experiment. And it's not always that you have good tools for doing it. It's getting better, but still, it's not easy, and it's also often very problem specific, so that's also the reason why there are not so many tools. But there are different approaches. One is code-free, so in principle, just by sorting the image into different categories, like organizing the images in different folders depending on what they have. You can also create an Excel file that lists all the features, like you have the image name and then you tell some information about it, like in the radiographs of the hands, you have the file name and then you have the age of the child. And for segmentation and object detection, then it's often about taking some kind of painting application. You can use, for example, Fiji or just your drawing application, and draw regions and save it as a separate black and white image. For that, there is a collection of tools that can be used. Just see the Tinder here. That's actually swiping left or right, depending on it's class 1 or class 2. That's a quite quick approach, but still, the swiping is maybe still 1 second per image, so you can get pretty sore in the thumb after a while. Here's another example that I did myself actually. Had a 2K by 2K image with a lot of white spots. This is just a little cutout, but you see these white spots, and we want to clean them from our images. And what I did was I was sitting there with my iPad and was drawing every spot, and it took 8 hours to mark up that image. No fun, but now I got it, and now I can at least use it for my tests. Then another way is to use simulations, depending on what you have. You can have geometric models, you can have some kind of templates, like already marked up objects that you start doing things to. You can also have really physical models. If you do fluid dynamics, you can actually already do some kind of pre-simulation and use that to create different test images. But it's always good to combine it with real data still. So here you can incorporate realistic information. And the advantage of doing a simulation is that you have really a ground truth. You know, this is what I had in the origin, and now I can degrade it and do bad stuff to the data. And that also gives you an opportunity to play more with the parameter range. And a very nice paper by this group is that they actually simulated an object, put it through a simulated, so they had a geometry with some faults in it, put it through a forward physics model for radiography, got some images, reconstructed it, and tried to segment and find the real result afterwards. So that's really the full workflow described here. It's a nice paper. I think that was just a conference contribution, but I think they have a later full paper on it too. And then we have some problems when we have our data sets. As imbalance, which I already hinted on before. We can have too few examples or too homogeneous. You only focus on one kind of very specific problem, but the world is much wider. And there could also be other problems. But first, looking into bias, as this one is quite an old example. I don't know if it's true really, but anyway, it went viral many years ago, where Google thought the people on that picture were gorillas. Anyway, looking at it, it may be fun, but for Google it wasn't very fun, and possibly also not for the people who were labeled gorillas. So their solution was actually just to remove gorilla category from their database, so they couldn't find any gorillas anymore. Then it worked out. The other way would actually be to add more and more examples to the data set. And here we come to the IBM diverse face data set, where you not only have people from different places, but also with different accessories or different hairstyles and so on. And that gives a much wider information in the training. And so here we have a little example. And in principle, it's just extracting 1, 2, 3 from our data set. And we can see in this case, we have a relatively homogeneous distribution, but the ones are dominant here. And this will be our data set for this little test. That comes soon. But another problem is when we have limited data, we can have, of course, yes?
One could consider like having, so if you have 3 outputs, like 1, 2, 3, you could consider like splitting the model and say, okay, I only are looking for ones, and I only are looking for 2, and only looking for 3, and get the probability, and then I like to compare it. And is there like an advantage?
You can. So there are different approaches. Right now, I'm just presenting what kind of data we have. Not so much into the algorithm, how to get them. I get a little bit to that, but they're much smarter things than I'm going to show today. Yeah, there are different approaches. One is plain and simple, just counting how many pixels you have, and that gives you some kind of regression probability that it's a 1, 2, 3. So there could be things like that, but algorithms comes later. So we can just very few data points, few observations. It's quite often that people coming to me doing experiments, they only have time to do 3 data points. Hopefully 5, but that's it, and possibly some variations around them, but that is the limitation of what they can get. Another problem is unbalanced data. So you have, example, one class, say the main population, they are healthy, no problem, and then you have some which have some disease, and they're very few. And it's not so easy to capture this imbalance, and if they are very distinct in the behavior in the data, then you can still capture them. But the problem is, if they overlap with the natural variation of the whole population, then it's just a little bump on the data histogram, and it's very hard to distinguish them. So that is something you have to look into, trying to balance the data or do something against this unbalance. And of course, you have little or missing training data. That can be handled by doing a lot of work. So, break is a good point. Yes. So let's take 15 minutes.